One of the main concepts that we need to know in Chapter 4 in order to add and subtract our fractions is what is a least common multiple. Okay. Least common multiple is the same thing as our least common denominator. But we need to be aware that if we don't have an actual fraction and we don't have a denominator, then the actual concept is just called least common multiple. Now, part of our issue with knowing what a least common multiple is the fact that we stop at the word least and we don't understand the entire title of what we are looking for. We're looking for a least common multiple. Now in the English language, the main concept, of course, is our noun. And in the English language, the noun is put after the descriptive words. The descriptive words are called adjectives. But we start with the noun at the end of our statement. Most of the other Romance languages put the noun, because it's the most important part of it, because it's that main object, in the beginning. So for an example, instead of saying blue house, they would say it's a house of blue, because the object is the house, and that's the important thing. The blue is secondary in describing that house. But in the English language, we put our nouns after the adjectives or the descriptive words. So we have to go beyond least. Think of least last. And least common multiple. The noun or the object that we're looking for is a multiple. Now we went through multiples last week. Multiples is taking a number times an integer and getting a result. So when we were learning our multiplication tables, we were learning the multiples of those numbers. So this is going to be a bigger number. Okay? When we're finding a least common multiple, it's a bigger number. Now, what type of bigger number is it? Well, then you look to the adjective that's closest to the noun to describe it. The adjective closest to multiple is common. Common. If something's common between or among the items, between two items or among three or more items, it's something that they share. So we're looking for a multiple, bigger number. We find our multiplication tables that the two numbers or the three numbers that we're comparing share, that they have in common. Now, which one is it? Well, this is when we realize that there's more than one common multiple to two numbers that we're comparing. So which of these common multiples do we want? That's where we go to the first word. We want the least or the smallest number that's bigger that they share. So we want the smallest. So let's just do a fairly easy example of 6 and 8. So what's the common multiple between 6 and 8? Well, one of the ways that you can do that is you can list out all the multiples. Well, obviously not all of them, but you can list out a fair amount of multiples of 6. 6 times 1 is 6, 6 times 2, 6 times 3, 6 times 4, 6 times 5, 6 times 6, 6 times 7, 6 times 8, 6 times 9, 6 times 10, and hopefully that's enough. And now we do the exact same thing with 8. 8 times 1, 8 times 2, etc. And we list those out. So now we have multiples listed of both numbers. So we've taken care of the noun. We've found multiples. Now we want to find the ones that they share. Oh, look through here and let's see here. Oh, they each have a 24. Oh, they each have a 48. And I'm sure if we had continued on, we would have found more of them that they share. So we have two different numbers that's multiples of 6 and 8 that they both share. So which one is our so-called answer? What are we really looking for? Well, we're looking for the least or the smallest one that they share. So the first number that they share is 24. So the LCM of 6 and 8 is 24. That's the first number that they share. Now that is one of the methods of finding the least common multiple, is to list out all of our multiples until we find the one that's the smallest that they both share, like we just did. But sometimes we have bigger numbers and it's harder to list out all those multiples. We're not very good with our multiplication tables if we get to a number that's beyond 12. And we don't want to just sit and do it by hand. And we don't want to use our handy dandy because we've got to use our brain a little bit. So we need to find another way, a trickier way, or a way of looking at it a little bit differently so that we can actually get our LCM. And so the second way is to use prime factorizations. We did prime factorizations last week. That's also known as those factor trees. You draw the little trees off of them. And we're going to use that to build the LCM. Now, if you recall from last week, the prime factorizations of each number is unique. That means that there's only one prime factorization for that number, and no other number shares that. But you'll notice that they share common factors. And so we're going to use this idea to build up a multiple that's common and small. So this is what we're going to do. We're going to find the LCM between 8 and 10. Now you could multiply and get 8 times 10 and get 80, but that's not the smallest one. And yes, we could list out our multiples because these are fairly small numbers and we're good with the multiples here. But I want to show us how we can use this prime factorization to find the LCM. We'll practice this on a smaller one and then I'll show it again on a little bit larger number. Okay? So the first thing we need to do is find the prime factorizations of our numbers. So we break down our trees. 8 is the same thing as 4 times 2. 4 gets broken down to 2 times 2. I can't break down 2's any further, so 2 times 2 times 2 is my prime factorization of 8. I'm just going to write that over here on the side. 8 is 2 times 2 times 2. Okay. And now we're going to do the exact same thing with the 10. Break it down. 10 we know is 2 times 5. Well, 2 is a prime number and 5 is a prime number, so I can't go any further with that one. Now what I'm going to do is I'm going to go over here and write that underneath the numbers that I have for my 8. So 10, I'm just using a colon to separate. You want to make sure that you don't include the actual number in this. Now I have a 2, so I'm going to line that up underneath a 2. Now my other number is a 5, so I'm just going to line this 2 up underneath the last 2 over here. And then I'm going to put the 5 beyond that. And the reason for that is, once again, because I want to line up the like numbers. I'm trying to find those common factors so I do not repeat them. So every number has essentially its own column. So now to find the LCM, we bring down a number from every column. Okay, so now here, this first column here is all 2's. There's just one 2 in that column, so I just bring that 1 2 down. Here's my second column of numbers. There's a 2 in there. I just bring that down. Here's a third column. Now these are also all 2's. Now here they lined up, so they kind of shared. We only want to write that 2 down once. It represents the 2's that are in that column. Okay? This is what's refraining us or stopping us from getting the largest possible number out there. We want the smallest. Remember, we want the least common multiple. So they both share a factor of 2, so we don't want to repeat it because that would get us a number that's too big. But every column has to be accounted for. So here's a column with a 5, so I need to bring that down. So my LCM is going to be 2 times 2 times 2 times 5. Well, now we just have to multiply that out. Now remember, for multiplication, it doesn't matter the order you multiply your numbers as long as every number is used once and only once. What I notice is that I have a 5 and a 2. We like 5's and 2's because 5 times 2 is 10. and that's an easy one to multiply with. Then I'm going to multiply these other 2's. 2 times 2 is 4. So now I'm left with 4 times 10. So my LCM is 40. If I had used both of those 2's, I would have had that 8 times 10, which is 80. 80 is not the least common multiple. It's a common multiple, but not the smallest one. And we want to find the least common multiple. So that's why we didn't want to duplicate the 2's. We wrote it only once, and that got us our least common multiple of 40. If you'll notice right here, as we write out our number, the LCM and all the factors, here's the 2 times 2 times 2, which is your 8. And over here is the 2 times 5, which was the 10. So both of the factorizations of our numbers are in the LCM because that's how we make a multiple. You have to have it's 8 times something to get this number. It's 8 times the leftover factor of 5. Here we have 10 times the leftover factors of 4 to get our LCM of 40. Let's try another one with some larger numbers. Let's find the least common multiple of 18 and 40. So we have to break down 18 and 40 into its prime factorizations. We have to make those factor trees there. 18, there's a couple ways you could do that. Doesn't matter what you choose first on your numbers as long as they multiply to your original number. So two numbers that multiply to 18, we like to go 2 and 9. 2 is prime, so we're all done with that branch, but 9 is not. We can break that down to 2 more branches of 3 times 3. Those are both prime, so we're done with our 18. Do the same thing with our 40. 40 is 5 times 8. 5 is prime, so we're done there. 8 is 4 times 2. 2 is prime, so we're done there. And 4 is 2 times 2. Now, to keep us a little bit centered on our board here, I'm just going to use the space. See, our 18 was 2 times 3 times 3. So I'm going to use the space here to rewrite that. 18 is 2 times, maybe we'll have a little extra space here. 2 times 3 times 3 is our 18. And our 40 has 1, 2, 3 2's. So I have 2 times 2, and this last one I'm making sure that I line up underneath one of the like terms above it, or like factors above it, and then I have a 5. Yeah, let me move that out of the way too. I don't want to line that up in a column of 3's, we only put like numbers in the like column, so I'm making another column for my 5 further over. And now to find our LCM, we bring down the numbers in the column. Only numbers of the same kind should be in a column. So anything that's in a column, I bring down. So I need a 2, I need this 2. I just need one number per column. So 2 times 2 times 2 times 3 times 3 times 5 is going to be my LCM. And now we multiply that out. Let's see here. 2 times 5 is a 10. 3 times 3 is 9. 10 times 9 is 90. And 2 times 2 is 4. 4 times 90 is 360. So the first number that they have in common is 360. If I had listed out all of these multiples of 18, I would need 18 all the way up to 18 times 20 to get my first multiple of 360. That's why it's nice to have this way of finding a common multiple instead of just listing out your multiples as our first option was. So when we have bigger numbers, what we want to do is break it down into their prime factorizations. Remember, those are the building blocks of the number. Every number has its own unique prime factorization. It's the fingerprint of the number. I think it's fantastic. A number has a fingerprint, something that's unique to itself. And so we're going to use that fingerprint to then build something that's common between two numbers. Now, why is it important to find the least common multiple? Once again, the least common multiple is the same thing as our least common denominator. So the application of finding an LCM is to get a common denominator, which allows us to add or subtract fractions. Before we can actually go through the procedure of adding or subtracting fractions, we need to make sure that we know what a fraction is and why we can't just add it all the way across as we would like to. Here I have drawn a nice little circle and I shaded in 1/3 of it. That's one part out of 3 total parts that would make the whole. That's going from noon to 4 o'clock. Noon, 4, and 8 help you. Okay, so it looks a little more like 4:30. I like the big 1/3. Okay? But that's what a fraction means. I have a small portion out of the whole. 3 parts would make a whole. I only have one of them. So I have 1/3 of the whole thing, which is a piece that's about this size if I had a circle or a pie or a pizza or some other yummy. Okay? And if I had that left over on one pizza, and over here I have a quarter left, I want to know how much pizza I have left. Now, a quarter, though, is a different size and shape because it's one part out of 4 total parts. So if I divide it into quarters, that's using noon, 3, 6, and 9 o'clock to draw out, you can tell that this piece that's shaded in here is smaller than the piece that I have over here. Because I have more pieces cut, having one portion of it is a smaller piece. Now, when we first learned how to add, we were adding 1 plus 1 is 2. Well, it wasn't just one item, it was 1 whole pie plus 1 whole pie makes 2 whole pies because and we could add those because they were whole items. It was that entire pie or that entire pizza, that entire object. Here we cannot add these together as they are because this is not the same size as this. And so how can I compare them if they're not out of the same denomination? Denomination. Denominators. We need to get a common denominator in order to add or subtract fractions. Think of it another way, like this. We know that 1 part out of 3, since I only cut it into 3 parts, I have a pretty big piece here. And 1 part out of 4, that's a smaller piece. So when your number in the bottom gets bigger, your piece gets smaller because you need to have more portions, more pieces to make the whole. Okay, so I need more pieces to make the whole. So I'm using red on this because this is not accurate. If I was just to add straight across, as most of us think that we should do, because it's easier, I would get 2 parts out of 7. Now, it just made sense to us that the more pieces we have, the smaller our portion. So this is saying I would end up having 2 parts out of 7. Now think about a circle being cut into sevenths. I don't know what sevenths is. Let's see here. 1, 2, 3, 4, 5, 6, 7. So it's going to look something like that, give or take. And now I only have 2 parts of that. So these pieces are all smaller than those. I have 2 of them. That's actually less than my smaller amount. How could I have this big portion here and add this other portion and get something that's smaller? Oh yeah, that doesn't really make much sense. That's why we cannot just add straight across. So let's get rid of that. That's bad. We have to make sure that the size of pieces that we're adding together are the same. We don't want a person to get more or less than the other. We want it to all be even in math land. And that's why we need to get what's called the common denominator, or LCD, least common denominator. Now the least common denominator is the same thing as that least common multiple that we just worked on. Okay, but now we are applying it. So which numbers are we finding the multiples that are common to? The denominator. That's why it's called the least common denominator. Now we're now looking at the denominator, the bottom numbers, and saying, oh, what's the multiple that's common, that's smallest for both of those? And we know that the first number that 3 and 4 both multiply into happens to be 12. So our LCD is 12. The least common denominator is 12. So now we have to use the information we've gathered from last week to find out how can I make this 3 into a 12. Now we need to make sure that the fraction is equivalent or has the same value as the 1/3, but now I want the denominator to be a 12. Well, last week we had something like 6/8, and we said, oh, there was a common factor of 2 in there, so we canceled that out because anything over itself is 1, and 1 times anything is anything to get our reduced fraction. What we're doing this week is the reverse. We're starting with something smaller and saying, hey, I can take this number times 1 and get the same number back. Any number times 1 is itself. But instead of just multiplying it by 1, I'm going to do a funky form of 1. So instead of it just being 1, I'm going to do something like this, in which it's some number over itself. Okay. So I can multiply. What do I multiply 3 by to get 12? 4. So I'm going to multiply the bottom by 4. But I can't just do the bottom because that would change the value of the fraction. Whatever I do to the bottom, I have to do the same thing on top. So I'm now multiplying by 4/4. Anything over itself is 1, so I'm really taking this 1/3 times 1, which will give me that 1/3 back, but because of the funky numbers here, it's going to have a different look to it. So that's going to give me 4/12. Right? Now, we can actually show it on the picture. I'm multiplying, I increased the number of cuts in my pieces here, and so I can now make now I have 12 pieces that would make a whole. I didn't shade any more. How many pieces do I have shaded? 1, 2, 3, 4. 4 parts out of 12 is the same thing as a 1 out of 3. I'm going to do a very similar thing to my 1/4. I need that to get a denominator of 12. And I'm going to multiply that by 3. Once again, whatever I do to the bottom, I have to also do to the top to keep it balanced. So that's going to make it 3/12. And once again, we're still adding, so I just put the plus sign in between. I can do that same idea here of, okay, I'm just adding those cuts in here. I didn't add any more shading, I just added more cuts to make it into more pieces, and I have 1, 2, 3 parts out of the 12 shaded. So now, in both of my pies, all the pieces are the same size. Because they're the same size, I can now add the pieces together. So we had 4 pieces over here, we're adding 3 pieces over here, so that's going to be a total of 7 pieces, but what's the size? When I add the pieces together, the size of the pieces do not change. So they're going to stay out of 12. So my answer is I have 7 pieces that are size 1/12. So I have 7/12 of the pie left. If we do all this work to get a common denominator, the denominator does not change when we're adding or subtracting. We only get common denominators when adding or subtracting. If this was a subtraction problem, it would be exactly the same, except on this last step, instead of adding the top numbers, those numerators, we would subtract them. That is the only difference between adding and subtracting. Everything else is the same. We have to get the common denominator, find out what that is. We might have to do those factor trees as we just learned in the LCM section to find out what is that common denominator. Then we multiply top and bottom So we say 3 times what gives me that common denominator. And that's what we multiply top and bottom by on that fraction. We ask the same question over here. Notice that we multiplied top and bottom by different numbers, but the top and the bottom would be the same here and the same here. Once we have the common denominator, we just add the top numbers and keep the denominator the same. That is how we add or subtract fractions. I'm not a big fan of mixed numbers because in algebra, we don't use a lot of mixed numbers. They don't make any sense to us. It's making us do work that we would then have to undo. Because if I need that number for anything, as we're going to discover as we're going forward here, I'm not going to be able to use it as a mixed number anyway. I'm going to have to convert it to an improper fraction. So why get an answer that's an improper fraction and then switch it over to a mixed number just to switch it back again if I need that number for something else? It's too many steps. We're not keen on doing that. So, and the other reason that we don't really care for them is this is a little bit messy. It's 20 2/3. Well, we could think of it as 20 times 2/3 in algebra because they're not exactly like and they're mushed together. It's just too confusing. We don't like to have all that confusion. So in algebra, we always keep our answers or our results as improper fractions, or a proper fraction if it comes up to that. But we don't change and we do not convert an improper fraction to a mixed number. This is a mixed number because it's a mixture of a whole number of 20 and a proper fraction of 2/3. A proper fraction has a numerator that's smaller than the denominator. An improper fraction, im is our prefix meaning not, it's like in, but because proper starts with a p, we change the n to an m so it flows better, that's why it's improper, means that it's not proper. If a proper fraction has the top number smaller than the bottom number, a not proper fraction means that the top number will be larger than the bottom number. So an improper fraction has it top heavy. Okay? And that's what we're going to do here is we're going to convert this mixed number of 20 2/3 into an improper fraction. The procedure is actually fairly easy to do. We just need to think of it as a circle and don't forget your final step. So you start with your denominator. Okay? And we're going to take the denominator and we're going to multiply it by the whole number. So we're going to take the denominator times the whole number. Okay? So in this case, we would have 3 times 20. Then we're going to add the numerator. Now, why do we take the denominator times the whole number? Well, we're trying to find out the total number of thirds we have. We know we have 20 whole pies and 2/3 of another pie. Well, if all 20 of those pies were cut into thirds, how many pieces would we have? And you get 20 times 3, or 60 pieces for those whole pies. And now we have to add, well, we also have a couple more pieces over here. So that's when we add the numerator. So we have the denominator times the whole plus numerator. Okay. But now we have to remember that this is still a fraction. And so in order to be a fraction, we have to have a denominator. So it's going to be all over the denominator. Right? Don't forget that you still have that denominator. So it's kind of cyclic. We start here with the 3 times 20 plus 2, and put it all over 3 again. So in this case, we had 3 times 20, which we just said was 60. Add the 2, and then put it all over the 3. So 20 2/3 is the same thing as 62/3. That is your improper fraction. Well, that's not so bad. So what's going to mess with us in this procedure? What's going to mess with us is negatives. What if I had negative 6 and 2/5? Okay. Now we need to remember that the negative is just telling us the direction that this number is. It's 6 and 2/5 in the opposite or in the negative direction. Okay. But in order to do the conversion, we don't use the negative. Think of that as it's the opposite. I want to find out what's the opposite of 6 and 2/5. Well, converting that to an improper fraction, we only use the fraction part. The negative just comes along for the ride. So I know my answer is going to be negative, but I do not use that negative in any of the calculations. I'm still going to take my denominator of 5 times my whole number of 6 and then add the 2. Put it all over the denominator. 5 times 6 is 30 plus 2 all over 5 gives me a final result of the opposite or negative 32/5. So the number was negative to begin with, so the improper fraction will be negative, but we do not use the negative in our calculations because we are 6 and 2/5 in the negative direction. Both the 6 and the 2/5 are in the negative. So if I was to multiply this, negative and a negative, it would make it a positive anyway. It's the opposite. It's just telling us that direction. So to convert from mixed number into an improper fraction, take your denominator times your whole number, add the numerator, and put it all over the denominator. If it's negative to begin with, your negative is also in the answer, but you do not use that negative in any of the calculations. So then the question is, how do we go in reverse? So now we want to convert from an improper fraction to the mixed number. As soon as the camera focuses. There we go. Converting an improper fraction to a mixed number. Okay? So if I have a fraction like 7/3, how do I convert that over? Well, you need to remember that a fraction is just a division problem. It's 7 divided by 3. Now remember the order that we're doing this. It's 7 divided by 3. The denominator is the number that goes on the outside. That's better. So we're converting the improper fraction to a mixed number, which is just a division problem. Now, if we did our division from week 1, we remember that we'd say, okay, how many 3's go into 7? That's giving us the whole number portion. We'd say, 2 3's go in there, so we put the 2 up above. We take that number and multiply. That gives us 6, and then we subtract. And we bring that down, we say 1. There's no other numbers here. Now in week 1, we said, this is my remainder. And to indicate our remainder, we said, big R1. So 7/3 would be 2 big R1. Now, we don't want big R1 anymore. We're going to take that one step further and say, what does big R1 mean? Well, it means that I have 1 part remaining out of 3. So the remainder becomes the numerator of the proper fraction. And the denominator stays the same just as it did the other way. So 2 big R1 really is 2 1/3. So to convert an improper fraction to a mixed number, we do the division top divided by bottom. So we're finding out how many of these go into the top, how many 3's go into 7. There's 2 wholes, and then the remainder becomes your numerator over that same denominator to write it as a mixed number. So if we have mixed numbers, what are the rules going to be when we multiply, divide, add, or subtract? So I wrote them all down nicely, and we'll just go through and make sure that you can read on the screen what I wrote. So mixed numbers. To multiply mixed numbers, the first thing you do is you convert to improper fractions. Then we go through our procedure for multiplying fractions, which, if you recall from last week, we reduce and multiply straight across. Or you can multiply straight across and then reduce, either one. Okay. To divide mixed numbers, the first thing we're going to do is convert them to improper fractions. And then we remember our rule for dividing is that you flip the second fraction, that's the reciprocal, and then you multiply. How do you multiply? You reduce and then you multiply, or multiply and then reduce. Okay. Remember, whenever you are reducing, you can only reduce when multiplying. Only time you can reduce. Okay. To add or subtract mixed numbers. Now your book goes through and explains how, if you're adding mixed numbers and you end up with an improper fraction, then you would have to carry, just like we carry with our addition. That's too complicated to remember. And if you're subtracting, it's, you can't take away, so then you have to borrow. Well, borrowing fractions is a pain in the watusi. So instead of that, I'm going to deviate from what the book says because this is going to be much easier. So when we add or subtract mixed numbers, the first thing you're going to do is convert to improper fractions. Then you won't need to know those borrowing rules or the carrying rules. Okay. But when adding or subtracting fractions, the next thing we have to do is find the LCD. Once we know what the LCD is, we multiply top and bottom of each fraction to get that LCD. Not by the LCD, but to get the LCD. What did I have to take the 3 times to get 12? What did I have to take the 4 times to get 12? That's what we multiplied by. Okay, so you have to find the LCD, multiply top and bottom to get the LCD, and then we can add or subtract the numerator, keeping the denominator the same. Once again, if we do all that work to get the denominators to match, they do not add or subtract in that last step. Those are the rules when we're dealing with mixed numbers. First thing, no matter what, convert to an improper fraction. This week we're also going to solve some equations with fractions. Let's get used to seeing those fractions in those equations that we're trying to solve for. So we're going to have to throw all the concepts together. The steps for solving is exactly the same steps that we used in the previous week, a couple of weeks, to solve. We have 1, 2, 3 terms up here. 2 of the terms are like terms because they don't have a variable. 1 of the terms is not like the other. We want to put the 2 terms that are like together, and we want to put it away from the term that it's not like, which means that I want to move this term over here. Now, this term, to move a term from one side of the equal sign to the other side, we use inverse operations, or the operation that would cancel or undo this. This is being subtracted. It's subtracting the 8/15. So to move that to the other side, we use the opposite operation of subtraction, which is addition. So we add the 8/15 to both sides. We didn't do anything with the 3/5, so that comes down. 3/5 x. Negative 8/15 and a positive cancel each other out, which is why we did it. On this side I have 2/15 and I'm adding 8/15. Now for some of us we can write it like that and we're fine. I always had the tendency to write my problem out horizontally instead of vertically like this so that I could see my numerator and my denominator. So instead of writing the plus 8/15 here, I would write it here. And now I can see my common denominator that I already have, and so I just add my numerator. It doesn't matter which way you do it, I'm just showing you that there is more than one in case we don't see it as clearly here. Now it's nice on this problem because our denominators are already the same. So now I can just add my numerators. 2 plus 8 makes 10, but remember it's still a fraction, 10/15. Now at this point, I would probably recognize that my fraction can be reduced. Whenever I can deal with smaller numbers, I like to do that. So I'm just going to rewrite this. It's 3/5 x is equal to, and what goes into both 10 and 15 is 5. So I'm left with 2/3. You don't have to do that step. If you don't see it, it's okay. It's just kind of nice that if you do, to make your number smaller. All right, so now we have to get the x by itself. Right now it's 3/5 times x. Notice that my x is really kind of in the middle here. It's not looking like it's next to the 5. That would be wrong notation. That would mean that you'd be dividing by that x, and we're not. We're multiplying. So you kind of keep it outside of the fraction and kind of along the middle. All right? Or if you're going to err one way, it's got to err on the top, not the bottom. Now last week we talked about how to get rid of that, and we would say, oh, we're going to divide by 3/5. But we know that dividing in fractions is the same thing as multiplying by the reciprocal. So I'm going to flip that and multiply, which means I'm going to multiply by 5/3. That's what the reciprocal is. That's because the 5 on top and the 5 on the bottom would cancel to a 1. The 3 on top and the 3 on the bottom would cancel to a 1. And 1 times x would just give me x. So if I multiply the left side by 5/3, I have to do the exact same thing to the right side. Multiply by 5/3. As I just stated, this stuff cancels, and I'm left with x is equal to. Now be careful here, you can only cancel things on top that match with things on the bottom. We don't have anything that matches up, so we just simply multiply straight across. 2 times 5 is 10, and 3 times 3 is 9. And remember, this is an algebraic problem. We do not convert that to a mixed number. We leave it as an improper fraction. Okay. Now, I like to solve my equations with fractions a little bit differently because we got lucky here in which we had a common denominator of 15, and so we could easily add that, but oftentimes that's not going to be the case. So then I'm going to have to get that common denominator and do all that extra work. I don't like to do all that extra work if I don't have to. So I have a second method in solving a linear equation that has fractions in it. Feel free to practice both ways and see what you are most comfortable with and go with that way, more comfortable with. This is what I do. I go through my equation and I say, what's my common denominator among all 3 terms? Among is used when you're comparing 3 or more things. Between is only used when you compare 2 things. So I'm going to find what would that LCD, that common denominator, be among 5, 15, and 15. Well, it's kind of nice that I have 2 15s. So it's 5 and 15, and between there, the first number that they both multiply into, bigger number, is 15. So my LCD is 15. Now, we've stated in the past that because this is an equation, I can do something over here on one side of the equation, and as long as I do the exact same thing on the other side, it's perfectly legal to do. It's perfectly balanced. So I'm going to do a little manipulation by multiplying both sides of my equation. What am I going to multiply by? The LCD. So I'm multiplying the top numbers, not the bottom, by the LCD. So I'm doing it the LCD over 1. So I'm going to multiply it, and it has to be every term on both sides. That's how we multiply everything on both sides. So I'm going to multiply this by 15. If you want to look at it as 15 over 1, you can do that. I'm going to multiply this other term here by 15 over 1. I'm just squeezing it in over here where I have some room. And then, of course, if I do this side of the equal sign, I have to do this side, so we multiply this side by 15 over 1. Now, why in the world would I do that? Well, let's look what happens when I simplify. I like multiplying fractions because we get to reduce and then multiply. It makes things nice and pretty. If I look at this first term, I have a 5 on the bottom and a 15 on top that's being multiplied. Remember, we can only cancel when we're doing multiplication of fractions. So since I have a 5 on the bottom and a 15 on the top, I can reduce. 5 goes into 5 once, 5 goes into 15 3 times. Now I'm left with 3 times 3 on top and 1 times 1 on the bottom. Remember, when we have 1s in the bottom, that's a really good thing because that's a whole number. Whole numbers are written over 1. So I don't need the 1 if that's on the bottom. So 3 times 3, that gives me 9. Don't lose my x. And I don't have a fraction anymore. Oh, what happens in the next term? 15 on top, 15 on the bottom, reduces to 1 over 1. I once again only have 1s on the bottom, which means I have a whole number. Don't forget that I'm subtracting. 8 times 1 is 8, equals, reduce here, 15 goes into 15 once, 15 goes into 15 once. I'm left with 2 times 1 on the top, and 1 times 1, which is just 1 on the bottom. So it's equal to 2. So by multiplying every single term on both sides of the equal sign by the LCD, the entire LCD, I just eliminated all of my fractions. And now I have a two-step equation that we learned in week 2. And the first thing we do, just like we talked about before, first thing we do, just as we talked about before, is to add the 8 onto both sides. Get those like terms together away from the term that it's not like. So I have 9x is equal to 10. And then finally we divide to get the x by itself. Get the 9 by itself. Make sure you show all of those steps so that you don't flip your fractions around. 9 over 9 is 1. 1 times x gives me x. And on the right side, there's my fraction. I don't have to do anything else with it except reduce it. Remember, reducing is not the same as converting. We leave it as it is, an improper fraction. So your answer is 10/9. So we can solve equations by doing your normal adding and subtracting and then dividing or multiplying by a reciprocal, leaving the fractions in. Or if you're not so comfortable with the fractions, you can multiply every term just on top by that LCD and it'll cancel and you'll be left with an equation with no fractions and you can solve that one. Those are your two methods that you can practice, get familiar with, and master one of them on solving equations with fractions. Finding an average. An average is simply add them all up and divide by how many you've got. Well, what does that mean? Well, here, say on the first day of the week, you did 3 math problems. And the second day, you did 7 math problems. But then you did 5 on the third day and 4 on the last day, which meant that you had to put it into gear, and so you did 11 problems on the last day. How many problems did you average per day? So approximately how many did you do each day? So in order to find that out, we're going to take each of these numbers and we're going to add them. And then we divide, so we write that as a fraction, by how many numbers we have. Well, how many days did we work on things? 1, 2, 3, 4, 5. We have 5 different numbers, so that's what we divide by. So now we add up the top and divide by that 5. Adding up the top, we have 9 plus 11 is 20. This is another 10, so that's 30. So we have 30, and we divide that by 5, which means that on average, we did 6 problems per day. Per means divide. Add them up, divide by how many you've got.